Welcome to the last lecture of week 7. This week we've spent a lot of time trying to learn symbolic execution and its advantages, disadvantages, and we specifically learned one algorithm for concolic execution, which is what is practiced, namely Dart. I will illustrate the working of that algorithm on an example today. But before we do that, I would like to spend some time looking at symbolic execution tool. What you see on the screen is the Wikipedia page on symbolic execution. And here is a section on symbolic execution tools. As you can see, there are several different tools. This full table is of symbolic execution tools. It gives the name of the tool. It gives the target environment, the programming language that it is for. There are a lot of tools for Java. There are some for JavaScript. There are traditional tools for Python and several other languages that you can think of. And where to get the tool from, this is given. And most of the tools are open source and downloadable. So that's the nice part about it. So this is quite a big table. And except for a few no's in this open source, most of them are yeses. So it just tells you that symbolic execution is very well practiced technique in software testing these days. And there's a lot of investment in terms of tools that go into doing symbolic execution. So if any of you would like to experiment more, that is outside the scope of this course, in terms of learning how symbolic execution tools for your favorite programming language works, this kind of resource will be useful for you all. As I told you, I will end this lecture on symbolic execution by illustrating how a concolic testing tool like Dart works for a programming language like C. So how does a tool like Dart work? What is a quick summary? Given a program that you would like to test to encounter and execute as many different execution paths as possible, you would like to subject the program to concolic testing automatically. That is, you would like to instrument the program, write a driver such that takes the program, figures out what are the inputs to the program, provides random values to the inputs, runs the program on these randomly generated input values, observes the path constraints, stores them, flips them as they are stored to explore neighboring program paths. In this process, it remembers whether all program paths have been explored or whether it has encountered an error, or there are some program paths that cannot be explored for whatever reasons, in which case it just goes ahead and substitutes concrete values for that. So this is a concise summary of how a concolic testing tool like Dart works. Suppose we have to apply it to C programs. How do we do it? How do you extract the interfaces and know what the input values to a C program are? How do you randomly supply the input values? That is the test driver. And how do you implement a directed search? Obviously, you implement the algorithm that we learned, but we'll just illustrate it through an example. So this is an example of a C program. I'm sorry, I squeezed it into the slide. It just about fits in. Some parts of it are jutting out, but you can read most of the program. So it's a program, a simple program that corresponds to a AC controller in C. So there are variables, a lot of Boolean variables. Variables like, is the room hot? If it's 0, then it means the room is not hot. If it's 1, then it means the room is hot. Is the door closed? 0 or 1. Is the AC on or off? 0 or 1. So initially the room is not hot. The door is open and AC is off. So all the 3 variables are set to 0. Then the AC controller takes a message, which can be a number. So message, as the code says, can be a number that is either 0 or 1 or 2 or 3. And based on the message, it does some actions. So if the message is 0, then it sets the room heat. Maybe the room heat is more. So it sets this Boolean variable is room hot to 1. If the message is 1, then it sets it back to 0. If the message is 2, it sets door to be open and AC to be off. If the message is 3, then it says close the door. And if the room is hot, then switch on the AC. And finally, if the room is hot and the door is closed and AC is not on, then you abort, which means there's an error. So this is a small program. We would like to explore all possible execution paths of this program automatically by using the Dart algorithm. It has several different if messages, not too many complex control paths. The part that I'd like to focus on is how to generate random values. There are several algorithms that are available, but we'll just see one way of doing it. So there are inputs that are initialized, that is these three variables, room being hot, door being closed, and AC being 0. So these are the inputs that are initialized. Then it identifies the external interfaces through which the program can obtain inputs via uninitialized memory locations. Here we don't have anything like that. There is this internal variable message, but here we don't have, but there could be inputs that are not initialized. So there could be several other external interfaces, like for example, the external variables, external functions. You could have undefined references, arguments of user-specific top-level function, which is called before the program begins its execution. All these external interfaces are obtained by source code parsing. You can use any kind of source code parsing by that. Inputs to a C program are defined as memory locations which are dynamically initialized at runtime through the static external interface. So when I run Dart for C, it has two ways of mapping inputs to memory addresses. One is several inputs can be mapped to a same address M, and they are obtained by reading M successively. That is, for each execution, you can read the value of M to get a value of a different input, or the same input can be mapped to different addresses in different executions. C has features for both of them. For each such external interface, we find out the type of the input and that is passed through that interface. And the thing about C is that types can be defined as basic types or as a struct type, which has one or more subtypes in it, and an array or a pointer and so on. So Dart distinguishes three kinds of functions specifically for C. One is program functions, which are defined as a part of the code. The other is external functions, which are called by the environment. So part of the external interface, they can return any value. We don't know what their value is. The other is library functions, standard library functions, which are not defined as a part of the application code that the developer has written, but they are used by the program, so they are a part of it. These functions also are treated as unknown, but we know what they return. So Dart cannot go inside them and look at their source code. So for that example that we saw here, this AC controller, here is a test driver that will randomly initialize values. So it says start, and to a certain depth you have this temporary variable, and do random initialization and call this AC controller on this temp. This test driver is basically another C program, which is what it is, which does the random initialization. The main function, this one, of the test driver initializes the external variable, all the arguments at the top level function by calling a random init. We'll see what random init function is. How many times you call it? It depends iteratively on how many runs the tester wants to do. And again, it contains code that simulates external functions in such a way that whenever an external function is used, a random value is substituted as the value returned by the external function. So this random init, which this main uses here, random init, how does it go? That depends on the variables of a particular type. So if the type is pointer, and then you initialize it this way. If the type is a struct, then you initialize it this way as you're given here. If the type is an array, then you go through a for loop and initialize the elements of the array. If it's a basic type, it is int or bool or string or character, then you assign that many bits corresponding to the size of the basic type. So random init basically does what Dart was supposed to do, but specifically for the data types of C. It takes a memory location M and the type of the value of the variable to be stored at the M, and initializes M with a random value that is consistent with its type. If M stores a value of basic type, its value star m is initialized with the auxiliary procedure random, which is what we saw here, this one. Random bits, which returns the random bits. If it's of a type pointer, then the location is randomly initialized with value null or with the address of the newly located memory location. That is this part here of type pointer. If it's a struct or an array, then all the constituent elements are initialized by going through a loop. That's what we've done here. For each such external variable or an argument to the first level function, Dart generates a call to this random init based on the type and feeds in random values. And then C program is being tested on calls that, or for the next part is the external function. Suppose we had an external function. Then the test driver generated by Dart will include a definition for this function. So it will just return a value as if the function was returning the value that is consistent with the return type of that function, whose code we don't know. That's what this piece is doing. So the test driver is generated. Now this will call the program under test and start running it. So directed search you can do by looking at the first few levels of the C compiler. In particular, you can use SIL language, which is used for parsing C code, or any other compiler. And you can use any constraint solver. When they wrote the Dart paper, the authors in 2005, they used this constraint solver called IPSolve. But now Z3 by Microsoft Research is a popular constraint solver. As I told you in the last module of week 6, pick up any solver that suits our need and then use it for solve. So this was a quick overview of what happens when a tool like Dart is run on C. So we are done with symbolic execution. In fact, we are done mostly with logic-based testing. There is no more to see as a part of this course. I'll quickly summarize what symbolic execution is. Symbolic execution is a white box testing technique that tries to execute a program to cover as many different execution paths of the program as possible. So in this process, instead of assigning concrete values to variables, it assigns symbolic values to variables and collects path constraints. At the end, solves the path constraints by feeding it to a constraint solver. Each solution gives rise to one concrete test case that drives the program through different execution paths. This inherent technique has some disadvantages because the path constraints could be very complex that they cannot be solved. Path constraints could lead to bounded number of paths, infinite number of paths. So people do concrete and symbolic execution intertwined. That is concolic testing. Concolic testing starts by taking a random test input, execute the program on that random test input concretely, simultaneously execute it symbolically, collect the path constraints that you encounter along this concrete run on the random input, flip the path constraints that you encounter in the order in which they encounter, and explore alternate programming paths. We specifically saw one algorithm like Dart that can do concolic testing, but now the state of the art is much more mature with lots of tools that can handle push button symbolic execution and concolic testing for several different programming languages. So the goal of this week was to introduce you to this niche area in software testing called symbolic execution. You're free to pick up further tools and explore them, but they will not be used for assessment in some sense. Assessment will correspond to what was taught in the lectures. So I'll stop here for now. This would be end of week 7. Next week, week 8, we'll start a new module that will involve black box testing. Thank you.